Welcome back, Algebra 2. We're in Lesson 104. Let's do a quick review of our complex numbers. We review complex numbers by remembering that a number like this, 4 over 7 plus the square root of 2i, is a complex number written in standard form. And standard form is where the imaginary number or the complex number is behind whatever fraction or integer you have as part of the answer. We often use the letters A and B to designate the standard form of a complex number by writing A plus BI. So that would be what's called standard form. And we use this form with complex, which includes numbers. Let me write that down. Numbers, which includes imaginary and radicals. All right. And that's radicals that we can't solve, right? So the square root of 2, square root of 3, right? Those are radicals we can't solve. We get crazy decimals if we do that. So this is what we would write for that. And we say that A and B can be any real number. Since 0 is a real number, either A or B can be 0. If B is 0, then only A is left. And so what we have is 4, 3 over 4, or negative 5 times the square root of 2, or negative 19 over 3. All of these are complex numbers whose imaginary parts are 0. If A is 0, then only the imaginary part B remains. Thus, the imaginary numbers negative 2i, 4 times the square root of 2 over 3i, negative 3i, and even just I by itself are all complex numbers whose real parts are equal to 0. All right, so if this is 0, we have these left. If this is 0, if A is 0, we have these left. That's really all that part of it is saying. And that's kind of just a review of what standard form is and what common sense equals to. Let's talk about subsets of the real numbers. So we know we have the real numbers. All numbers are real numbers, right? So we have this like umbrella. That's, not a really great umbrella, but it's what I got. So we have this umbrella system, right? And real numbers is a part of the umbrella system. Now over here, our real numbers are all numbers. Over here in this little section, we have irrational numbers. They're kind of all by themselves. But a part of real numbers is the rational numbers. And rational numbers include repeating or terminating decimals and fractions. Underneath that, we have what's called integers. And those are positive, negative numbers, and 0. And then underneath the integers, we have whole numbers. Whole numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And then underneath that, we have natural numbers. And natural numbers are just the numbers that we use to count with. The only difference between the whole numbers and the natural numbers is that the whole numbers include 0. Natural numbers start with 1. Whole numbers start with 0. So they're kind of in the same group, but we just put 0 in with the whole numbers. And what I like to think about the difference between the two, if you look at it, you have your natural numbers, which are, right, 1, 2, 3, 4, 5, yada, yada, yada. And then you have your whole numbers, which is a 0. If you think about it, 0 is a whole. So whole numbers equals 0 plus the natural numbers. All right, that's just the way my brain works. If it helps you to remember, then that is awesome. If not, hopefully my little weird umbrella sketch will help you remember that as well. And that is how we categorize the numbers in our number system. And of course, everything is based off the base 10 Hindu-Arabic system. Irrational numbers cannot be represented exactly with decimal numbers that contain a finite number of digits. For instance, the square root of 2 is an irrational number and can only be approximated with a decimal numeral. A pocket calculator will give you an approximation of the square root of 2, and it'll say that the square root of 2 is something like 1.41421336. The complete representation of this number would require a number with an infinite number of digits. It's non-terminating decimal, and as you can see, it's a non-repeating decimal as well. So if the digits in a decimal terminate, the number is a rational number. If the digits in a number don't terminate, but they repeat in a pattern, then it's a rational number. So that's why we say the rational numbers are non-repeating, non-terminating decimals. And that would include the square root of 2. So let's look at example 104.1. We're going to show that 0.00314 is rational by writing it as a fraction of integers. So here's how we do that. So all we're going to do is we're going to count the number of decimal places we have. 1, 2, 3, 4, 5. So we say 0.00314 times, and then we're going to multiply 10 to the 5th because we have 5 decimal places, and 10 to the 5th. Okay, so that's going to equal this number, 314, over 1 with 5 spaces. So this will be 1 over 100,000. So because we can write it as a fraction in its entirety, it is a rational number. We have just proven that this decimal number is a rational number. Any number that we can write as a fraction is a rational number. Let's do one more. 104.2. We are going to show this number as a rational number. And we have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 zeros and 6, 2, 3. So let's show it as a rational number. So we have 1, 2, or let me count this way. 1, 2, 3, 4, 5, 6, 7, 8 decimal places. So times, and then we say 10 to the 8 over 10 to the 8. So that would be 623 over 1, 2, 3, 4, 5, 6, 7, 8. We put in our commas, and that is 100 million. 623 over 100 million. That's it. We've shown it as a fraction. So we've proven that decimals can be expressed as rational numbers pretty easily. We just have to count their decimal places and put them over the appropriate place value. So let's see if we can do the same thing for repeating decimals. Can we turn those into fractions? I think with a little manipulation, you can see that we can do that. So we indicate that digits in a decimal fraction repeat by drawing a bar over the repeating digit. So for instance, let's just take this first one. 0.01623, and we indicate that this one repeats the 2 and the 3 over and over again by putting a bar over the 2 and the 3. Each of these, let's write the other one that they have here. They have 1.03114, 1, 5, 4, 3, and they have that 5, 4, and 3 are the repeating digits. Each of these represents a rational number, and any rational number can be written as a quotient of integers or a fraction. That is what a quotient of integers is a fraction. So to write it, we must get rid of the repeating digits. We can eliminate the repeating digits by subtracting it from the product of itself and 100. So what we'll do is we'll multiply this number times 100, and we'll set it equal to 100n. So if we multiply this by 100, we get that we move this over 2 decimal places, right? So this would be 1.6232323. This repeats, right? So now we'll say n is equal to 0.0162323, constantly repeating, right? It's constantly repeating. So therefore, if we were to subtract these from one another, we said 100n minus n, we'd have 99n is equal to, and if we subtracted these, you see how these are lined up perfectly to subtract from one another. So each of these would cancel out. So all the repeating decimals would be gone. So we would be left with these to actually subtract. And that would give us 1.607 is equal to 99n. So now we just divide both sides by 99. But we can't have a decimal over a fraction. That just doesn't work. So we're going to multiply by the number of digits we have here. That would be times 100. So that would be times 100. I'm sorry, 1,000. 1, 2, 3, 1, 2, 3. And times 1,000 here on the bottom. We know we can multiply by the top and the bottom and retain the same value in a fraction. So this does not change anything. It just makes it to where the decimal goes away. And then we say 99, 1, 2, 3, put in our comma. We have now written this as a rational number, as a fraction, or what we call a quotient of integers. So this number is now expressed as a rational number. So with just a little bit of manipulation, we can show that a repeating decimal is in fact a rational number. So let's try it with this one. So if I say, let's see, with this one, I'm going to use, we have 3 repeating digits here. So I'm going to need to multiply it by 1,000. So let's do, 1,000. So 1,000 n is equal to, I'm going to move this decimal place, 1, 2, 3, 4. I'm sorry, 1, 2, 3. So 1, 0, 3, 1. And then there'll be a decimal here, 5, 4, 3, 5, 4, 3. All right, and n would still be the same, 1.0315543. So you see it's all about the number of digits that you have here that are repeating. Here we had 2, so we used 2 zeros. Here we have 3, so we're going to use 3 zeros. So now we know that these repeating decimals are going to constantly line up with one another, so they will subtract from one another, right? And then we make that negative. We make this negative. We just basically multiply both sides times the negative 1, which we know retains the same value. So now when we subtract, we get 999 n is equal to, and if we do the math, we get 1,002.1512. If we then divide both sides by 999, we know that we can't leave it in a decimal form like this. We have to multiply it times the 4 places, 1, 2, 3, 4, 4. Had a hiccup there. and the bottom by the same number. So we know the top and the bottom by the same number is okay. So n is equal to 1002, 1512, and then we put our commas in the appropriate location. And then we have 999 and 4 zeros, 1, 2, 3, 4. Put our commas in the appropriate location. And now we have expressed that number as a quotient of integers or a fraction. Easy peasy. It just takes a little bit of manipulation in order to express them as a fraction, and it is still the same number, because if we did the division here, we would get this decimal again. So let me show you. If I can pull it up. So let me pull, let's do this first one. 1607 divided by 99, 123. 0, 1, 6, 2, 3, 2, 3, 2, 3, 2, 3. It's the same number, but expressed as a fraction, right? Same thing over here. 1002, 1512 divided by 999, 1, 2, 3, 4. Same number. 0. I missed a 0 when I wrote it down. 0. Did I? Yes, I did. It should have been 2 zeros. That was just my mistake in copying it from the book. So it should have been 2 zeros right here. So sorry. So that would make sense now with the 1002, right? Yeah, I bet you're looking at that going, Miss Tracy, your math is off. It was just I didn't copy it down correctly. So yeah, it's the same number when you divide it as your repeating decimal up here. So let's try and do one on our own. And we actually, this was 104.4. So let's do another one. Let's do 104.4, 104.5. I'll eventually say it right. Okay, let's clear the page. We'll do 104.5. And we are going to show 13.012 with a repeating decimal of only the number 2. We're going to show that as a rational number. So we know that this is a single repeating digit, so we only need to multiply it by 1 0. So that would be 10n is equal to 130.1222, right? The original number is going to be 13.0122. All right, we're going to multiply both sides by -1. We know that all of these repeating 2's are going to cancel each other into an infinity. So the only thing we have to actually subtract is right here. And we're going to do that in the calculator. So let me clear that out. So if I have 130.12 minus 13.01, I get 117.11. Right, and this becomes a -9. I'm sorry, not a -9, a +9. 10 minus 1 is 9n, and what did I say that was? 117.11? Yes. All right, so 117.11. If I divide both sides by 9, I know we can't have a decimal in a fraction, so we multiply by the number of decimal places I have, which is 2, top and the bottom. So n is equal to 11711 over 9 and 2 zeros. So 11,711 divided by 900. And if we check our answer, 11711 divided by 900, we get the same repeating number, 13.01222222. So we did that correctly. We set that up as a quotient of integers, or a fraction, and a fraction is considered a rational number. So that is how we can prove that a repeating decimal is indeed a rational number. Very, very good. All right. If you have any questions about that, if you want to know what we're doing, we're actually just reviewing our complex numbers and we're exploring why the number system is what it is and why we consider terminating and repeating decimals to be rational numbers, and that is why. And that's all we have for lesson 104. I will see you all in lesson 105.